Hello everyone, myself Mr. Elemental, and today I am here to welcome you to the Essence of Geology, an open platform. Today we're going to discuss a really interesting topic. Yes, you can see it on the screen. It is the structure of metamorphic rocks. So there is a diagram, which is a diagram of the rock sample that is amphibolite. So before going to the structure part, we need to know what is a metamorphic rock. So basically we can say that metamorphic rocks are those rocks which have been formed through the process of metamorphism that took place on the pre-existing rocks. That means the primary rocks under the effect of changing temperature, pressure and chemically active fluid. That means the phenomena through which the metamorphic rocks are formed is known as metamorphism. Thus, metamorphism is a process involving changes in mineral composition or we can say microstructure of the rock, dominantly in solid state under the effect of temperature, pressure and chemically active fluid. That means the process of metamorphism usually takes place at solid state. That is the difference. Now, as we have already discussed about the primary and secondary rocks, yes, metamorphic rocks are secondary rocks. The process, which is the metamorphism process, means this process is such a process that took place, or you can say that it occurs as a response of the rocks to the changing environment, especially in three factors: the change in temperature, the change in pressure and the change in chemically active fluid, or you can say sometimes the presence of chemically active fluids. Now, plastic deformation, recrystallization of mineral constituents and development of parallel orientation are typical characters of metamorphic rocks. They are megascopically distinguished from the other rock types from the development of features like cleavage or foliation, schistosity, granulation, etc. etc. Now, metamorphic rocks are generally formed at great depths, and some beautiful examples of metamorphic rocks are like slate, phyllite, quartzite, amphibolites, etc. So here you can see two figures. The first one is showing a sample of slate and the second one is of course showing a sample of phyllite. Now let's come to the next part, the texture and structure. So textures are small scale features in a rock that are penetrative, which means that the texture occurs virtually all the rock bodies at microscopic scale. Now, texture of metamorphic rock depends on the shape of the minerals, their modes of growth and mutual arrangement. But on the other hand, structure is a term used for large scale features that occur on the hand sample, outcrop or even regional scale. Now, structure of a metamorphic rock depends on the interrelation of various textures within the same rock unit and are frequently dominated by the directive forces due to the unequal pressure. That means the overall texture eventually represents the overall structure of the rock. But though terminologically differentiating or distinguishing the texture and structure in case of metamorphic rock is a quite simple thing, but believe me, on the field or at a practical level, it is quite a tough work. Now, there is another very useful term in this context is fabric. Now, what is fabric? The fabric is a term that is usually used to describe the microstructure of a rock, which partially includes both the textures and structures, but it's a more useful term in practical uses as there is both structural and textural features present in metamorphic rock altogether and could not be studied any one of them by ignoring the other one. That means the use of the term fabric is much more practical compared to the use of the terms like structure and texture when the question is about working on the field in case of metamorphic rocks. Now, let's discuss two more important terminologies. Those are the foliation and lineations. Simply, any penetrative set of more or less parallel surfaces, or we can say any planar fabric element, can be termed as foliation, as you can see in the first diagram. And any penetrative set of more or less parallel lines, or you can say linear fabric element, can be termed as lineation, as you can see in the second diagram. So why these terms are important? Foliation and lineations are such things, you can say, those actually affect in both structure and textural context. That means in both megascopic and microscopic scale. So studying them is quite important if we are trying to reach the foothill of the knowledge about the texture and structure. And if we want to move up to the peak of that mountain of the knowledge about structure and texture of metamorphic rocks, then we must study the foliation and lineation at a larger scale. Now, types of foliations. According to Turner and Weiss in 1963, there are 8 different types of foliations. You can see the first one, that is the compositional layering. The second one, that is the preferred orientation of platy minerals. And then the third one is, of course, the shape of deformed grains. You can see in the diagram, that is the C. And so on. The rest of them are present here. You can see them. And if we talk about the types of lineations, you can see the 6 different types of lineations. 5 different types of lineations present in the diagrams. So the first one is preferred orientation of elongated mineral aggregates. Then the second one is preferred orientation of elongated minerals. As you can see, there is not that mineral aggregate present. So the rest 3 are also present. You can see them in the figure. Now, let's come to the main point. That is the specification of the structures. So the first one is the cataclastic structure. The cataclastic structure is characterized by the development of extremely fine rock mass under the influence of severe crushing and shearing effects of stress operating during metamorphism. The effect may be observed in rocks spread over wide areas, and rocks like crust breccia, mylonite, and slate show this type of structure. That means these kind of rocks are they're more prone to showing this kind of structure. That means the cataclastic structure compared to the other rocks. It simply doesn't mean that the other metamorphic rocks do not show the cataclastic structure. They also, of course, show it under the specific circumstance, the environment that is suitable for the formation of this kind of structure. Now, these rocks are mainly formed under the effect of shearing stresses in the upper zone of earth crust. The already produced cataclastic structure is actually produced under the stress and in absence of high temperature, whereby rocks are subjected to shearing and fragmentation. Only the durable minerals partly survive the crushing force, and the less durable ones are powdered. Thus, when the resistant minerals and rock fragments stand out in pseudo-porphyritic manner in the finer materials, it is known as something porphyroclastic structure. And when rocks are highly crushed into fine-grained rocks, they are called as mylonites. Since all these structures are formed due to cataclasis, they are as a whole known as cataclastic structure. Now there you can see one diagram, one figure of a regional level scale in which the rocks are showing cataclastic structure. Let's go to the next part, which is the schistose structure. So it is one of the most obvious structural features of most of the metamorphic rocks, and it is generally described as the alignment of platy or flaky mineral in parallel layers. The rock with schistose structure is made up of broadly parallel or subparallel layers of flaky, platy, or rod-like minerals, making it very weak in the direction of parallelism. Here, the platy or flaky minerals like micas and other equidimensional minerals show a preferred orientation along parallel planes under the effect of stress dominating during the metamorphism. The longer directions are parallel to the direction of maximum stress. That means the schistose structure basically describes the direction of maximum stress, rocks named as schist typically show this type of structure. That means we can also say that those rocks which typically show the schistostructures can be termed as schist. Now, the foliation of the schist is known as schistosity. Here you can see one diagram of a rock that is showing the schistostructure. The ideal temperature for the formation of schist ranges from around 600 degrees C to 850 degrees C, and the pressure ranges from 3.5 kilobar to 8.5 kilobar. Now, here are two samples showing schistostructure, and especially the second one in which the schistosity is something folded. And you can see that in both the pictures and also the former one, the parallelism, the alignment of the platy or flaky minerals in a specific direction, and they are showing a specific certain parallelism with each other. Now let's go to the next part, the gneissostructure. So you can see in the diagram that's a biotite gneiss from Norway. The sample is collected from Norway. So in this structure, bands or folia, you can say folia, the term is very useful. So bands or folia of platy or flaky minerals alternate with those of equidimensional and granular minerals. These bands generally are of contrasting color, composition, and sometimes texture. The presence of gneissostructure is an indication of advanced degree of metamorphism under combined action of high temperature, pressure, and active participation of fluids. Now, most of the time, the rock is characterized by alternate dark and bright colored layers. The light colored bands are generally composed of quartz and feldspar, whereas the dark colored bands are composed of primarily the ferromagnesian minerals. Now, gneisses typically show this type of structure, hence the term is used as gneissostructure. Or you can say those rocks which show the gneissostructures are known as gneiss or gneisses. Now, if we talk about the ideal temperature at which the rocks formed which show gneissostructure, generally form it always greater than 973 Kelvin, and the pressure ranges from 4 to 5 kilobar. Here are two diagrams. The first one is a garnet gneiss. The second one is a gneissic structure in a rock that is most probably from Karelia. And the first one is of course from Lamo Lake in Amazon. Now let's move to the next part, which is the Mekulose structure. So this is a kind of structure that is characterized by spotted appearance of rock that may be caused due to the formation of large size crystals, or you can say porphyroblasts, within an otherwise fine grained rock. This structure is typical product of thermal or contact, you can say metamorphism, and results generally due to incomplete recrystallization of the constituent minerals. It is formed by thermal metamorphism of argillaceous rocks like you can say shale. With increasing degree of metamorphism, the spotted slates pass into extremely fine-grained granular rocks known as hornfels. So here you can see a rock sample, which is a hand sample actually, that is showing the Mekulose structure, the spotted appearance. But there is another very closely associated structure, or you can say very similar kind of structure shown by many metamorphic rocks, and this is the Oggen structure. So what is the Oggen structure? This structure is typical of metamorphic rocks in which the effect of crushing under pressure is clearly associated with recrystallization. Now, in this kind of structure, some of the resistant minerals get deformed into thin lenticular lens-shaped shapes. They took lens-like shapes, giving a characteristic appearance to the rock, as you can see in the diagram. This is an Oggen structure in a rock found in Lake Alamo of Arizona. There is another structure then comes, it is the slaty structure. So it is also termed as slaty cleavage. This structure is commonly developed in rocks like shale, which usually have undergone slight metamorphism. Rocks showing a slaty structure are very fine grained and composed mainly of microscopic flakes of minerals like mica. This structure is caused due to parallel orientation of flaky minerals, mainly mica and chloride-like minerals. So these structures may be formed at any angle to the old bedding planes of the shale or any other argillaceous rock from which it was formed, which the slaty rock have been derived. Now you can see a diagram of a rock in which the slaty structure is clearly defined. Now, there are various opinions regarding the structures of metamorphic rocks. Here, I want to pick another very important structure which is quite controversial because some geologists consider it as a structure, some consider it simply as a texture, whatever. I want to say something about it. So, this is the granulose structure. So granulose structure is a typical structure of some metamorphic rocks and is characterized by an essentially granular character of the constituent minerals. The individual grains be irregular in outline but are interlocking. Foliation is absent or negligible. So they break with a rough fracture surface. Rocks with granulose structure are termed as granulites. Now, this is found in rocks containing equidimensional minerals like quartz or feldspar or pyroxenes. They are generally formed by the recrystallization of pre-existing rocks under uniform pressure but great heat. That means the heat is quite high. Temperature is quite high. The typical structure is coarsely granoblastic. These structures are also known as saccharoidal structures. Now, quartzite and marbles are typical examples of rocks which show the granulose structure. Anyway, I want to conclude with some very important things that why the structure and texture of metamorphic rocks is necessary. I mean, why the study of structure and texture of metamorphic rocks is necessary, because if we try to find out the structure and texture of a rock, actually we are trying to find out the change in environment and that at that time where and when that rock was formed. That means let a structure have a schistostructure. Sorry, my mistake. Let a rock have a schistostructure, and if we are able to study its structure and of course its texture, then we will eventually find out that under which condition this rock was formed. And if we can find out that specific environmental change at that specific time at which that rock was formed at a specific place, then eventually we are looking into the past. That means how the environment was changed at that time. That means the structure and texture of a metamorphic rock can explain us a total environmental condition that was present at a specific time under which that rock was formed. So it is basically a window for us to see what happened at the past. Thank you for watching the video. If you like it, then please hit the like button and please share it so that our fellow friends or admirers of geology can also watch it and can take help from it and also can help us in knowing more things. That means if you find something wrong with our video or our information, then please notify us in the comment section. And if you need additional informations, then please visit our website www.essenceofgeology.com. Please say us that how our information collection was. Was it right? Was it perfect? or simply it may be total wrong. So if we are wrong, please say us, because we can improve ourselves if you help us. If you need additional information, then please visit our website www.essenceofgeology.com, and please subscribe our channel because more are coming. Thank you.